Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss another application of Laplace transform, that is the solution of simple harmonic oscillator and damped harmonic oscillator can be evaluated by using Laplace transforms. Let's begin. First, for simple harmonic oscillator, we know the restoring force for simple harmonic oscillator is equal to minus kx, where k is a constant and that constant is known as, that is the force constant, or we can say it as spring constant. And the negative sign so that the restoring force is directed opposite to the displacement x. That is x, that represents the displacement of the particle from the mean position. So the equation of that SHM can be written as the restoring force, that is a force, so mass into acceleration, mass of the particle, let small m, acceleration d square x by dt square, second order differentiation of the displacement, is equal to minus kx, or m d square x dt square plus kx is equal to 0. That is the equation of motion. This one is the equation of motion of simple harmonic oscillator. And its initial condition let the condition initially be given by x at 0 is equal to x naught, and its first order differentiation x dash at 0 is equal to 0. These are the initial conditions for the equation of motion simple harmonic oscillator. Let us solve that kind of differential equation. To achieve the solution of equation of motion of simple harmonic oscillator, we have to introduce Laplace transform concept. Taking Laplace transform on both sides of equation 1, taking Laplace transform on both sides of equation 1, we get, so m is the constant, Laplace transform of d square x dt square plus k Laplace transform of x is equal to Laplace transform of 0, which one is equal to 0, or m Laplace transform, and the second order differentiation of x plus k Laplace transform of x is equal to 0, using the formula for the derivative of Laplace transform as m s square x dash minus s x at 0 plus k Laplace transform of x x bar 0, or expanding the bracket m s square x bar minus m s, so x at 0 is equal to x naught plus k x bar is equal to 0, or dividing m on both sides, s square x bar minus s x naught plus k by m x naught is equal to 0. Rearranging as s square x bar plus k by m x bar minus s x 0 is equal to 0. Let us substitute omega naught square is equal to k by m, s square x bar plus omega naught square x bar minus s x naught is equal to 0. So x bar taking common, we have s square plus omega naught square, and that term to this side x naught into s. Our requirement x naught x bar is equal to s x naught divided by s square plus omega naught square. Now we take the inverse Laplace transform to get the solution of the differential equation. What be the value of x? So taking inverse Laplace transform, taking inverse Laplace transform, we get L inverse of x bar is equal to inverse Laplace transform s x naught divided by s square plus omega naught square, or inverse Laplace transform of x bar, which was equal to x, is equal to x naught constant to outside inverse Laplace transform of s divided by s square plus omega naught square. That one is nothing, the inverse Laplace transform of that term is equal to cos omega naught t. That one is the required solution of simple harmonic oscillator. X is the displacement of the particle from the mean position. The equation of motion for simple harmonic oscillator, its initial condition, we solve the differential equation by using Laplace transform. To achieve x, we take the inverse Laplace transform on both sides, and finally the solution of SSM, simple harmonic oscillator, x is equal to x naught cos omega naught t. Next, for damped harmonic oscillator, how we calculate the solution for damped harmonic oscillator? Same thing. In case of damped harmonic oscillator, there will be the two force, one is restoring force, another one is damping force. The total force due to restoring force plus damping force. In damped harmonic oscillator, the contribution of force due to both restoring as well as damping force, that is total force is equal to restoring force plus damping force. To take that of equation of damped harmonic oscillator, total force, that is mass into acceleration. So mass m of that of particle, acceleration, second order differentiation of that displacement d square x by dt square is equal to restoring force, as we discussed, minus k into x, and damping force, which is unequal to minus b into v. As we write it, damping force proportional to the velocity acts on that body. So the damping force, that is the b, the constant, and the velocity to that of body, where v is the velocity on that body. Therefore, m d square x dt square is equal to minus kx minus b for velocity, first order differentiation dx by dt. Therefore, the equation of damped harmonic oscillator will be m d square x dt square plus kx plus b dx by dt is equal to 0, or m, that is the second order differentiation of x double dash plus kx plus b, first order differentiation of x single dash 0. Rearranging, m x double dash plus b x dash plus kx is equal to 0, at equation number 1. That equation, this equation is known as the equation of motion, the equation of motion of damped harmonic oscillator, damped harmonic oscillator. The initial condition, the initial condition for the equation for damped harmonic oscillation, x and 0 as x naught, and its first order differentiation at 0 is equal to 0, which implies first order differentiation. So, dx by dt will be 0 at time t is equal to 0. That one be the initial condition for damped harmonic oscillation. This is the equation of motion for damped harmonic oscillator. Now, we have to evaluate that differential equation by using Laplace transform concept. So, taking Laplace transform on both sides of that equation number 1, taking Laplace transform on both sides of equation 1, we get m Laplace transform of x double dash plus b Laplace transform of x single dash plus k Laplace transform of x is equal to 0. We use the formula of derivative of Laplace transform. So, m, that one is equal to s square x bar minus s x at 0 minus x dash at 0 plus b s x bar minus x at 0 plus k x bar is equal to 0, or m s square x bar minus m s, put the value of boundary condition as x of 0 is equal to x naught. So, x naught plus x dash at 0 is equal to 0, that term b s x bar minus b x at 0 x naught plus k x bar is equal to 0, or x bar as common m s square plus b s plus k is equal to m s plus b into x naught. To that side we take the terms having x naught. Therefore, x bar is equal to x naught into ms plus b divided by ms square plus bs plus k, or x bar is equal to x naught into taking m as common, so s plus b by m divided by taking m as common, we have s square plus b by m into s plus k by m is equal to x bar is equal to x naught, cancel out, s plus b by m divided by s square plus b by m s plus k by m. Next, or x bar is equal to x naught into s plus b by m divided by, we write that term as s plus b by 2m whole square plus k by m minus b square by 4m square. Taking its square, we have the term s square plus b square by 4m square plus b by m as 2 cancel out, and adding that term we have that denominator term. Here we put that value, putting omega 1 square, let k by m minus b square by 4m square. Therefore, x bar is equal to x naught into s plus b by m divided by s plus b by 2m square plus omega 1 square is equal to x naught divided by s plus b by 2m square plus omega 1 square into, in that of numerator term we have s plus b by 2m plus b by 2m. In place of b by m we write b by 2m plus b by 2m. That x naught is multiplied to the terms written as x naught s plus b by 2m divided by s plus b by 2m square plus omega 1 square plus x naught b by 2m divided by s plus b by 2m square plus omega 1 square. Now, x naught s plus b by 2m divided by s plus b by 2m square plus omega 1 square plus x naught b by 2m let omega 1 divided omega 1 multiplied. There will be no such change, divided by s plus b by 2m square plus omega 1 square. It equation number 2. That for x bar, to achieve the value of x, we have to take inverse Laplace transform. Therefore, taking inverse Laplace transform on both sides, we get L inverse x bar is equal to x naught inverse Laplace transform of s plus b by 2m divided by s plus b by 2m square plus omega 1 square plus x naught to outside, b by 2 m omega 1 also outside, as that terms as constant. Inverse Laplace transform of omega 1 divided by s plus b by 2m square plus omega 1 square. Therefore, inverse Laplace transform of x bar is equal to x, which is equal to x naught its inverse Laplace transform e to the power minus b by 2m into t cos omega 1 t plus x naught b by 2m omega 1 its inverse Laplace transform sin omega 1 sin omega 1 t into e to the power minus b by 2m whole into t. Rearranging the terms as x naught e to the power minus b by 2m whole into t as common. In that of bracket we have cos omega 1 t plus b by 2m omega 1 sin omega 1 t. Which is equal to x naught e to the power minus b by 2m into t. Here taking the LCM, the term as 2m omega 1. So, 2m omega 1 cos omega 1 t plus b sin omega 1 t. Here we can use a simple concept, that is for x is equal to that expression with the solution of damped harmonic oscillator. From that of damped harmonic oscillator, we can also achieve for simple harmonic oscillator term. How? When b is equal to 0, b is equal to 0 means there will be no such damping. In the absence of damping, there will be no such damping force. So, x is equal to x naught divided by 2m omega 1, b term 0, e to the power 0 is equal to 1. Here 2m omega 1 cos omega 1 t as 0, 2m omega 1, 2m omega 1 cancelled out. We have x is equal to x naught cos omega 1 t, as we expect, which is expected as the solution of simple harmonic oscillator. If there will be no such damping, then from that of expression for damped harmonic oscillator, we can easily reduce the simple harmonic oscillator equation. So, with the help of this video lecture, we understand the use of Laplace transform for simple harmonic oscillator, the equation of motion for simple harmonic oscillator and its boundary conditions, and its solution by taking Laplace transform. That is the solution of simple harmonic oscillator. Next, damped harmonic oscillator. Here is the force due to restoring force and damping force. That is the restoring force. That one is the damping force. This is the equation of motion of damped harmonic oscillator and initial condition. Then using Laplace transform and proceeding, putting some substitutions, and finally to have the solution by taking inverse Laplace transform on both sides. This one is the solution for damped harmonic oscillator. From damped harmonic oscillator equation, we can easily convert to that of simple harmonic oscillator when the damping is missing. That equation is reduced to simple harmonic oscillator. In this way, we studied how Laplace transform is useful to evaluate the solution of both simple harmonic oscillator and damped harmonic oscillator. So, with this useful and informative notes, let me wind up this session. Thank you.